Yeah. Thank you so much for the introduction. Thank you so much for the invitation. I'm very excited. I don't know if the volume is right for the recording, but I'm very excited that you guys are trying to understand this field, and certainly has been moving and claiming many things over the last, I would say, 5 years. There are like many things that the press has been saying about artificial intelligence. So I will try to give you an overview of first what artificial intelligence means, then the history of artificial intelligence, and what today's artificial intelligence may have for us for the near and maybe far future. Like, is artificial intelligence going to kill us all? that's some of the things that some people are saying. So I'm from the I School. It's a School of Information Studies at Syracuse University. I studied computer science, and then I moved into cognitive science and psychology because I wanted to understand how humans think and how maybe I can bring that knowledge into computer science to make computers act more like humans. I mostly fail at those things because the human mind is actually very complicated. Of course, I was very naive, but I realized that a lot of tasks that are very easy for humans were actually very, very complex for computers to solve. Like this basic idea of detecting what kind of animal a picture might have is something that was very challenging for computers. Okay, so and then I move into trying to understand more of the neuroscience, how the actual neurons work, more of the actual implementation of intelligence, and I also didn't move too much forward. And then I move into kind of try to understand how science itself works and how to use big data sets to try to understand trends in science itself. So I've moved quite a lot for different fields. So I have a very general view of artificial intelligence. But if you have questions about particular parts of artificial intelligence, about the psychology, the cognitive science, or the neuroscience, I'll be happy to answer them. And please interrupt me if you think it's appropriate. Okay, so I'll start. This is the outline of the talk. I'll start by the definition, and as you can imagine, people think different things when they talk about artificial intelligence. Now, there are hundreds of definitions for artificial intelligence. And I'll try to give you a sense of what most artificial intelligence researchers mean when they talk about artificial intelligence. Okay? Then we'll go through classic artificial intelligence, because this concept was actually coined in the 40s, so it's not something new. I mean, it's relatively new compared to other fields like mathematics and biology, but it's something that was coined 60, 70 years ago. So we'll go through those discussions. And then we'll see that artificial intelligence as a field died out because funding was removed, and so for 20, 30 years, there wasn't a lot of research in the area. And then over the last, I will say, 10, 15 years, there is a resurgence of this term artificial intelligence because of things that we'll see. Yeah, and then I'll go into some ethic problems, some discussions about how these machines may pose threats and introduce biases into all kinds of things, from legal system to just basic to finance, all kinds of things, health and things like that. Okay, and then what we might have for the future. Is artificial intelligence going to kill us all? Okay, so as he said, if you Google artificial intelligence, this is the definition that you get. Okay, so first line of Google will say, artificial intelligence is the theory and development for computer systems that are able to perform tasks that normally require human intelligence. Okay, such as visual perception. That means looking at a picture and understanding what the picture has. That it has people, that it has furniture, all those things. Speech recognition. The idea that you're receiving the sound waves of what I'm saying, and you are somehow, to some mysterious process, transforming that into sentences and into ideas. And decision making, how you take uncertain goals that you want to, let's say you want to arrive here to the center, how you start from your home and you make the decisions, each of the steps to drive here and decide what time you're going to wake up, all kinds of things that you have to decide when you make these sequential decisions. And lastly, translation, right? How you translate Spanish into English or your English into Chinese or something like that. So those are tasks that were typically done by humans forever, right? From the entire history of humanity, these were tasks that we thought only humans were able to solve because of the complexity of it. Okay, so that's the definition of Google. But as I said, there are many different definitions of what artificial intelligence may mean, and I will review a couple of them. And they mostly cover what people have meant by artificial intelligence in the past. So the first definition, and it is taken from a book called Artificial Intelligence, A Modern Approach. Okay? So the first one is, at the beginning almost of the field, it was this idea of that an artificial intelligence agent was an agent that acted as a human. Okay? And this idea was proposed by Turing. This was a researcher from UK. He was fundamental in proposing the theory behind computation and all kinds of things that I won't get into. But he said in one of his many amazing discoveries that for us to regard a computer intelligent, it will need to pass the following test. And he proposed this, what we now call Turing test. And this is the test. So a computer passes the Turing test, the intelligence test, if a human interrogator, after posing some written questions to this computer, cannot tell whether the written responses come from a person or a computer. Okay, so that was a very simple but actually very complicated proposal, because to solve this problem, you will need to solve many different aspects of artificial intelligence. So let's think about this. So you can imagine that sometimes you are chatting, like, I don't know if you put, I complained, I think, to Spectrum the other day. I wanted to complain about how bad my internet was, and there was this chat room on the website, right? So you start chatting with someone, but sometimes I wonder if the person I was talking to was a human or a computer, because I would get this, thank you for your answer, this is very nice of you, and I was saying some random things. So I couldn't really tell if some of the answers were coming from a computer or a human. Okay, so that's kind of the idea. You will enter a chat room, you wouldn't see the other person, and you will chat for a while. And if you couldn't tell after 10 minutes, or, I mean, Turing didn't really define a time frame, but he said you cannot tell if the person behind the chat room is a human or a computer, then the computer passes the Turing test. So that was it. Now, this already has many challenges, right? At the time, this is in the 50s, okay? This is a long time ago. Computer science, neuroscience, we didn't really have a good understanding of this field. So the first challenge was taking text, right? So we write a question, natural language, that's what the natural language processing concept means. You would take naturally written text as you would write a letter or an email, and the computer will need to understand what you mean, right? Are you asking something? Are you stating a fact? Are you making a claim? Like, what are you saying with that text? That's very challenging already, and there is active research in the area. Then, let's say if I wanted to, let's say I could ask the computer, where is Manlius, right? So the chat will need to realize that Manlius is an actual physical location. It's not a person. I'm not asking where Manlius, Acuna is. I'm asking where the location Manlius is. So I will need to realize that it's a location. Then it will need to access a knowledge base to map that location into a location in the US. So, and the answer presumably will need to be Manlius is located in Manlius, New York, close to Syracuse or something like that. So it involves several tasks already. This is not what people mean, professional people working on artificial intelligence mean with artificial intelligence. Now this is interesting as a concept. Many people have worked on this to try to solve these tests, to try to come up with a computer that will pass this test. But this is not what people mean. Now let's review another potential definition of artificial intelligence. This is the idea that we want to not just create a computer that will fool another human, but we want to understand how humans think. We want to get inside the human mind, and we would like to understand what are the processes that the human mind is carrying out to produce behavior that is artificial, that is intelligent. Okay, so this idea of thinking humanly, of more of the cognitive science side, is how is the mind, what are the mechanisms that the mind is using to achieve this intelligent behavior? And you can have several levels of this. So the first level is how are the inputs, like how is the light, let's say, of this room, hitting on my eyes, then transforming that light into electrical signals that go into the back of my brain, because here's the visual system of my brain, and the brain somehow transforms that into connections to other neurons, and then for some mysterious process that gets transformed into an understanding that this room is full of people and I'm giving a talk and all that stuff. So that process is one way of trying to understand this question, right? Like how is the implementation of intelligence being done? Another level could be, okay, what are the steps that I'm taking to recognize that I'm giving a talk and I recognize that this room is full of people, right? So what are the things, let's say this is more of high level understanding of intelligence. And then there is even a higher level that is the computational question, like what are the goals that I'm trying to achieve when I'm giving a speech, or what are the goals of you coming into this talk, right? So again, this approach tries to understand intelligence from the inside, right? So it doesn't look at artificial intelligence something that you want to design or create without regarding of how actually intelligence works in humans. Yet another definition of artificial intelligence is this idea of thinking rationally, thinking logically. So, and this would be the idea of how we, starting from either naturally occurring, let's say, axioms or principles that we have when we are born, let's say, how do we take those principles and we derive new knowledge? Okay, so if you have some mathematical background, that means that how do we take, let's say, axioms or principles and we combine them to produce new theorems, let's say. Okay, so as an example here, let's say we may be born, or we may be taught that all humans are morals. I'm a human, Daniel is a human, and then the new knowledge that we can derive is that Daniel is moral because he is a human as well. So the idea of thinking rationally was this idea of taking principles and then combining them to create new knowledge. Okay, so this is one vein of what people meant artificial intelligence in the past. But I would claim that most people use the term artificial intelligence to mean an agent that is acting in a world. This is a very general definition. So we have an artificial agent that is performing actions in the world, and this agent has some sort of rational goal. Okay? So every action that the agent takes, or every sequence of actions, is evaluated at some point. Okay? How good we are from a certain goal or objective. Okay? So there is a rational component on it. And this is, again, very general definition. So some components of the Turing test, for example, fit into this. Some components of logic fit into this idea. Some components of cognitive science also fit here, because from cognitive science, let's say, we might want to understand how humans perform tasks, how they want to achieve goals, and then we can get inspired to create rational agents. Okay, so most researchers, when they talk about artificial intelligence, they generally mean this idea of having an agent that is learning and that is trying to maximize some goal or maximize some benefit. Okay? Now, the good thing about this definition is that it's very concrete, in the sense that it's very easy for a computer scientist to take this and put it in actual code, and then programming the machine to learn using this code, to have a function that at the end of trying different things can evaluate how well it's doing. Now, I've been very abstract until this point, so I will give a more concrete example of how this all may play out in reality. Okay, so classic computer programs are written step by step by an expert. Okay, so if I want to, let's say, have a program that achieves some tasks, sends email, or computes the taxes or whatever, usually you will, classically, someone will write a program, all the steps very precisely, and it will give that program to you, and then you will run it many, many times. Right? So the program will take an input, follow the steps, and then create an output. And this is pretty much similar to how a cookbook will work, right? So we have an expert cook. He or she came up with an amazing recipe for an apple pie. So the cookbook, you have the steps precisely laid out. You have how much flour. I never actually baked an apple pie, but so I messed up some of the steps. So you take the flour, the batter, I suppose some milk, and then you let it rise, and then you put it together in some sort of a recipient, some sort of place, and you put some butter on it, and you put fruit, right? So you follow these steps, and then the result is going to be this beautiful apple pie, crispy, and all the things that I personally buy at Whitman's for $5.99 or something. Okay, so this is how classical computers program work. So how would an artificial intelligence program work for something like this? Well, not all of the steps will be put into the computer program. Okay, so it might have a skeleton of how, let's say, how to get the input, how to produce the output. Okay, so the input might be, okay, I'm gonna grab all the ingredients that are in my kitchen, and the output is going to be whatever I take out of the oven. Okay, so those might be the only hard-coded steps that I put in my program. And then the program has rules for, this is a very, very strong simplification, but it might have rules for combining, let's say, all the ingredients in random steps, right? And then having some parameters of how well to combine some things, what to put first, things like that, okay? So the computer program, this artificial intelligence program, will start combining these steps, let's say at the beginning randomly, and then we'll put some random stuff into the oven, and then the last step, we'll take this out of the oven, and let's say the first time we try it, we might get this thing that it doesn't even look like an apple pie, but this, let's say, might be our first result. But the cool thing is that we have, because we are acting rationally, we have some sort of evaluation step. Okay? So at the end we ask, is this good? Does this taste like an apple pie, or is this yummy, and is this sweet, is it crunchy, all the things that we think are good about apple pie? Probably not that good. So the computer will think, okay, what did I mess up? Let me go back and kind of rethink what are the steps that I messed up. So I might try again. Let's say the next time it puts too much fruit, so now it's old, you have a huge layer of apple, and the crust doesn't look too appealing. But there was some learning, there was some modification that actually created something that at the end might be like, this is not too bad. It's not, this guy, don't throw it away. I may eat, I might put it somewhere to go with whatever with my lunch or something. And then you might try again. Maybe now the apple pie inside is good, but then you put it too long in the oven, and then it was all burned. And inside is good, but then to eat it, you have to remove all the things that are on top. And you can imagine that you can repeat that many, many times, and at the end you will come up with some sort of good-looking and good-tasting apple pie. So this is the general idea behind artificial intelligence. Classically, you will put all the steps of the recipe very, very precisely, but artificial intelligence programs figure out some of the steps by themselves. Okay, so they have, and there are many, many ways in which this is done. Okay, so how am I doing on time? I don't know what time is it. 10? Okay. So is it an hour? Sorry.
An hour is fine. If you could take it a little bit longer, people want to move to that way, ask the questions that they might understand what they're questioning, and your response.
Okay, good. Okay, so we'll now go into what classic artificial intelligence was. Okay. So in the 40s, the computer science department didn't really exist as we know them today, or as they exist today. So all the fields of computer science and all the different like hardware and software and all the things that we know computer science has today didn't exist at that time. So computer science didn't exist. Neuroscience wasn't really a field. The idea of studying information in a theoretical way didn't also exist. So many of the things that these days we think about as being part of collaborating with neuroscience, with artificial intelligence, were not there. Okay? But the interest in trying to understand intelligence was there. But all the people that were trying to do this were from mathematics or engineering or biology, right? But they didn't really have a place where they can express these ideas of trying to create artificial agents. Okay? So in 1956, there was this seminal workshop at Dartmouth College, and the goal of the workshop was to take the leaders of each of these fields, mathematics, of information theory, biology, that were thinking about these ideas of creating artificial agents, take them, bring them for 2 months, and brainstorm what could be, let's say, a research program to think more about this idea that everyone was thinking about but didn't have a name yet. Okay? And at that time, I think a couple of years before 1956, the term artificial intelligence was coined. Not because I think if you read the person who coined it, which I forget right now, I think was someone called with last name McCarthy. He said, okay, this name is because so at the time there were many different names trying to achieve the same thing. So he created a name that was almost it wouldn't cause too much trouble. Like people wouldn't complain too much. So it was artificial and it was intelligent. So it didn't make people in psychology mad or people that were doing cybernetics mad. It was trying to be very very nice to other people. So and they say, okay, we are going to work on artificial intelligence. Now this workshop, in this workshop were around 10 people. But really, there were two researchers from Carnegie Mellon who stole the show because they had several concrete computer programs that blew everybody's mind. Okay, so these two fellows are Hermann Simon and Alan Newell, and one of the things that they show was this program that will take axioms, let's say axioms of trigonometry or something like that, or and let's say. And just simple axioms, and the program will automatically search possible solutions, let's say for the triangle inequality or some simple theorem. Okay? And the system will automatically derive the steps necessary to prove those simple theorems. Now we look back and say, okay, this was just a simple search that it will take just milliseconds for a computer to solve. But at the time, the idea of giving some initial steps to a computer program and then letting the computer program solve the intermediate steps was very revolutionary. Okay. Now this was amazing for everybody, and Simon is quoted saying, "We have invented a computer program capable of thinking non-numerically and thereby solve the venerable mind-body problem." Okay, so this idea that how we can connect the mind, which was this idea of how the humans think, how the artificial is, and then the body, how to actually carry out the steps to produce a result. And those quotes kind of look a little silly these days because it was really a very simple search algorithm, but again, at the time, it was something really revolutionary. In 1962, a researcher called Frank Rosenblatt produced a proposal of how to make neuron-like units, how to put those units into a computer program. At the time, the computers were not really like we know them today. They were more like vacuum tubes and big rooms with a lot of noise. That's what computers were. But he devised a way in which the simple neurons will connect to each other to achieve a task and will learn from mistakes. Okay? And I will show you a video that displays how this computer program worked, and it was called the Perceptron. Okay. Now, hopefully this will work.
In the 1950s and 60s, scientists built a few working perceptrons, as these artificial brains were called.
He's using it to explore the mysterious problem of how the brain learns.
This perceptron is being trained to recognize the difference between males and females. It is something that all of us can do easily, but few of us can explain.
Sorry. I was enjoying the video on my screen and you guys couldn't see anything.
In the 1950s and 60s, scientists built a few working perceptrons, as these artificial brains were called.
He's using it to explore the mysterious problem of how the brain learns.
This perceptron is being trained to recognize the difference between males and females. It is something that all of us can do easily, but few of us can explain how. To get a computer to do this would involve working out many complex rules about faces and writing a computer program. But this perceptron was simply given lots and lots of examples, including some with unusual hairstyles.
But when it comes to a beetle, the computer looks at facial features and hair outline and takes longer to learn what is told by Dr. Taylor. Andrew Cruikshank's wig also causes a little puck searching.
After training on lots of examples, it's given new faces it has never seen and is able to successfully distinguish male from female. It has learned. While promising, this approach to machine intelligence virtually died out.
Okay, so that was the perceptron. As you saw, the research was putting actual pictures. So the device will read that picture and will pass it through through a set of connections. You see my mouse? But it's to a set of connections. So these were just functions that will take the inputs, let's say the intensity of each of the pixels, the intensity of the positions in the picture, and combine them together, and will produce an output that will be yes or no. Is it a male? Yes. And if no, then it's a female, for example. Okay. So at the time, as you saw, this was a computer, so it was a very big room, and it learned by just looking at a bunch of examples. So the researcher will put hundreds of these pictures, and it will say, is it male, is it female? And the computer will automatically build by a process called, by some simple calculus, rules from calculus, it will modify itself, modify the function to be more precise at predicting whether it was a male or female. So the computer program will look at many examples of males and female pictures, and then the researcher can put, let's say, the Beatles, someone from the Beatles, and the computer will actually correctly predict that, even though at the time the hairstyle of the Beatles were not the most common one, it will still predict that I think was Harrison or someone like that was male. So when people saw these kind of capabilities, and when funding agencies saw these kind of capabilities, they were like, oh my God, this is the future, this is amazing. Okay? And Hermann Simon, again, was quoted in '57 saying the following: "It is my aim to surprise, it's not my aim to surprise or shock you, but the simplest way I can summarize is to say that there are now in the world," listen to this, "there is now in the world machines that can think, learn, and create." This was '57. "Moreover, their ability to do these things is going to increase rapidly until, in a visible future, the range of problems that they can handle will be coextensive with the range to which the human mind has been applied." Okay, so, yes?
So, reading through this phraseology, the guys at Google were attached to this concept somehow, some way.
Yes, so, but this Google is, these days, it's not back then.
I'm talking about their search engineering of the way that they had to understand this artificial intelligence and some mechanical understanding for them to be doing and to create this dynamite search concept.
Right.
And the guys, anybody, the Bing guys, the Yahoo guys, all these guys that were in this, to search, had to understand this.
Well, this quote is claiming that machines will think, learn, and create. Okay, so those are very high-level functions that we all agree humans can do, right? We can write books, we can paint, we can create music. And this is 57. They were thinking that at the time, these simple machines could do that. And I don't think Google was thinking about having computers creating web pages, let's say, in the 90s, where they were created. So these were claims about almost the very essence of what humans can do. So, and Google certainly improved a lot of the search functionality, but the aim of Google wasn't really to create a machine that will do these things. Okay? So Simon at the time made a prediction that in around 10 years, for example, let's say in 1967, a computer program could win against a world chess champion. Okay? And it will prove a mathematical theorem that will be significant. Okay? So these things didn't really happen until much later. So Deep Blue won against Kasparov in 98, 97, so it really took more than 40 years to achieve that, to something like this. And the theorem proving, I think, was achieved in the 95 or something like that. But it wasn't really, these were not really computer programs that will say, okay, these are acting like humans. So a couple of years later, someone proved that the Perceptron, the video that I showed, that little machine, actually couldn't solve very simple problems. And it showed that, let's say, for problems where the division between, let's say, male and female was very hard for different categories, for example, for different breeds of dogs, which sometimes is very hard to distinguish between. Then for those problems, this Perceptron wasn't able to solve the problem, and will never actually solve it and will never converge to a solution. So this paper was published in, I think, 66, and it killed artificial intelligence for 30 years. Okay? So, and there were many other problems in many different countries that actually show that, okay, all these crazy claims about what artificial intelligence could do couldn't really be realized. Therefore, we're going to just remove the funding, and I'm sorry, just do something else. So for almost 30 years, research in artificial intelligence, of this goal of creating artificial intelligence, died out. Now, what happened after that, this was around at the end of the 70s, was that people thought, okay, let's bring back the human, let's bring back this expert, and give us the rules that we should put into programs. Okay? So remember that the goal was to remove the expert, let the computer learn by itself almost everything, and those programs didn't really work. Okay, so during these years of AI winter, it's called actually, the AI winter, researchers brought back humans into the equation. Now I will show you how modern artificial intelligence looks like. Okay. Okay, so let's look again at this problem of detecting the category of a picture. Okay, so when we show a picture to a computer, remember that the computer is not looking at, you know, shapes or colors. Like all these concepts that we as humans describe very easily are actually very hard to describe, because the computer just only sees, you know, bytes, just zeros and ones. There is no really description of color or anything like that. We can make up these concepts, but it's not really there in the data. Okay, so let me show you a couple of examples. I don't know if you can see well, if it's the contrast is good, but Can you guys tell me what animal is this one in the first picture? Fox? Dog? Fox? Okay. What about what about this one? What about this one? Let's say.
What happens if you make it bigger? You zoom in.
Well, I cannot. Is that better?
That's better.
Okay. What about this one?
Nope.
It's a ram.
Ram. Okay. Good. Okay. What about this one? What about this one?
Owl?
Sorry. It's funny, yes.
No wonder the machine's having a problem.
Okay, so some of them are easier to see. Like the first one I show, some people say it's a dog, a fox. It's actually a fox. I'm sorry, the image is small, but it's you at least recognize it's some sort of a animal, right? You didn't say this is a car or something like that. Now, getting an answer like that for computers 15 years ago was very hard. Like having a computer look at this image and coming up with a classification, say this is a dog, this is a fox, this is a hook, this is whatever, like this is a Labrador, this is a, I don't even know what that, this is a ram. Those answers were really hard to get from computers, and for good reasons, because many reasons, but basically 15 years ago, the models, the computer models that we used to solve this problem were very simple. These days, a task like this can be solved by a computer better than a human. So a computer, there are tasks right now that allow a computer to classify an image into around 1,000 categories, different dog breeds, different animal species, and things like that, which is very complicated for humans. Now the pictures that I showed you at the top were easy classes, because computers have a very and computers and humans have a very easy time predicting this. These are hard tasks or hard classes. So in 2011, where this data set was published, the performance of machines was around 25% error rate. Okay, so 1 in 4 classes they will get wrong. Now that's not bad, because there were around 100 or 1,000 classes. So if you pick randomly the class that an image belongs to, you will get like 99% error, right? So 25% error is not that bad. What happened over the next couple of years was that machines and these techniques that people were using to classify images got better and better. In 2012, it was 15% error rate. 2013, it was 10%. Then 14 was 5%. Human level performance on a task like this is around 5%. 2 years ago, the performance of the classifiers, machine classifiers, got to around 3.5%. Is that scary?
Are we talking about something like IBM's Watson?
Something like that, yes. So IBM Watson is a little bit, it combines different sources of information. So first it needs to understand the question, like the text, then it needs to grab from a big knowledge database the information, and then it needs to disambiguate. So it has more steps. So it is the same idea, but it's in a different plane, let's say. So it's a more specialized task, if you will. Now let me show you another example. So here I have a picture of somewhere, I think this is in the Netherlands or some place in Europe. And there is this machine that can take any famous painting from a famous painting. I don't know who painted this, what artist painted this right here. But the machine can take the picture that you take, and it can apply the style of any famous painter. And then produce a picture, the original picture, with the style of this painter. And here we have, I don't know the painter. I know that this is Van Gogh, so let me just go with this one. So this is a screen from Van Gogh. And Van Gogh has a very distinctive way of painting, like this long stretch, and I'm not an artist, so I'm just, you can see Van Gogh painting and you can immediately recognize it. Okay, so you can say, okay, apply the style of this picture to my humble picture taken in Europe, and then the computer program will produce something that looks remarkably close. Now, I was so proud that I came all the way from Syracuse here that I want to introduce you to my parents. They said they wanted to say hello. So this is my dad. He said hello. Thank you for inviting my son Daniel. This is my sister. He said thank you so much for the invitation. We are very proud of my brother. This is my older brother. He had some problems with his hair. This is me. These are all me. It's all me. That's the picture I took on the top left. And the machine, after learning through millions and millions of pictures of what a female looks like, what an older person looks like, and what a bold, I think this is called Hitman Style, what a hitman looks like, it applied those effects to me. And it's amazing, right? I actually look like my father. I actually look like my sister. This is true. I don't have a brother that is bald, but probably it's pretty accurate. Amazing. This is an app that is on my phone, and it's called Face App.
If you were working in a secured place, would the computer pick out between you being a man and you being a woman? Would that pick up on that, or would it confuse the computer?
That's a very, very good question. I'm actually proposing a grant exactly on that idea, because now these pictures can fool humans, some of them. And we don't know the answer to that. And there is a big concern in the security community that a lot of these new techniques will produce fake data that is indistinguishable from real data.
I mean, the police are doing this sort of stuff with,
exactly.
Lost kids, whatever,
Exactly.
they aged them, people, whatever, so, but whether or not you could really confuse the computer or, fool it.
Yeah, it's a very good question, and we don't know.
With the computer's possibilities, why are we considering going to Mars?
What's the question?
Why are we considering sending a person to Mars when a computer can do all of these things?
Well, that's also a very good question, because can computers do all the things that humans can do? And I don't think they can. No? So this is a little bit of the hype that I see sometimes in the news. Like, you see all the time news articles claiming that we are all gonna die and computers are gonna kill us next year, and we should all just enjoy our life because we don't need to care what's gonna happen. We are all gonna be taken over by the computer overloads. But I think there is a lot of these are very, very specific tasks. Okay? And what humans can do. Remember, we have the same hardware, we have our human brain. The scale of the human brain is really orders of magnitude more complex than the computer programs that did this. Okay, so in terms of scales, we are not there yet. In terms of the capabilities, computer programs can solve a handful of tasks. So these tasks, aging someone or making someone be a woman, are very specific, very narrow. We need a lot of data to do this, so we need thousands and thousands of pictures to teach the computer what a woman looks like. And they can really generalize. We cannot take, okay, can you take this idea and apply it to make someone younger, let's say? No, we can't. We need hundreds of thousands of pictures of children to do that. So we can't really take what we have learned from here and apply it to some new domain. So that's the challenge these days, how you translate knowledge that you have in one specific domain into another domain. Okay, so I'm going to show you an AI machine that generated music in 2014. It's a little bit mellow, right? It's a little bit like 2014. This is 2016, 2 years later. I'll just stop it there. But you can immediately see that the sounds, that there is a longer arc of the sound. If you like music and classical music, you see that you have, more complex, longer range motifs in the music. And the 2016 computer program can actually generate more complex arcs of movements of music. So it's pretty, and this is a company that is trying to generate a computer program that creates music. So why is this happening? Why is this happening? Why do we have this amazing result when in the past, computers could barely, solve anything that we thought we're good at? Like you see now Google Translate, you see Siri, you use your cell phone to recognize your voice. I have a funny accent. And in the past, computers couldn't recognize my funny accent because, but now they're pretty good. I can say, hey, take me to Manlius library. And Siri said, hey, I'm gonna take you there. It's gonna take you 15 minutes. You went to take a coffee on the way, and I actually did that. So my funny accent is recognized these days, whereas 10 years ago, it wasn't. So what happened? Well, what happened is that people realized that data was very important. So the amount of data that we had available 60 years ago, like let's say the number of pictures of men and women that we have available 60 years ago, it was in the hundreds. These days, Facebook, Google, they have access to millions and millions of pictures. So they can have computer programs that are much more complex, and they can make many, many more mistakes, and therefore learn better. That wasn't dramatic, right? They can learn better. Okay? So the data that we have is what's driving really the advances in computing, in artificial intelligence. Yes?
If the computers have gotten to that level, why can't they be used in some place like Puerto Rico, which had a big disaster? Why can't they come in and after 2 weeks have it running, have the electrical back? If we have that knowledge, why isn't it being used?
Yes, so that's a very good question. Why can we use amazing results in these domains and bring them into something that has real implications? And again, the problem is that we need data. Let's say we want to solve the problem of blackouts. We need a lot of data about blackouts. We need a lot of data about hurricanes to make computers learn. And we don't have that data. So we need a lot of data from narrow domains to make them work. And there are certainly efforts to make these into more applicable applications. So for example, there are some companies now trying to have computers detect cancer in pictures. So you have an app in your cell phone you can take. I have actually a funny thing here in my skin, so I'm a little worried. So there is this app that you can take a picture and you can say, hey, this looks a little worried, you should go to a doctor. So instead of spending hundreds of dollars going into a skin expert, I don't even know the name, but yes, so you can take a picture and it will classify pretty well. So the data that we have available, and also the training and the computing power that we have available really driving what's happening, okay?
So how do you drive all that base data?
Well, that's why the people that are driving these amazing results are people that have available all this data. So Google, for example, they have available speech. They have hundreds of thousands, millions of hours of people talking to their phones. They actually record everything you say to your phone because they want to use it to train better programs.
I like your example that the computer artificial intelligence can be used to modify, or I'm sorry, to eliminate certain things and then have a human being look at the end. For example, the photos, I mean, I try to use photos, Google Photos, to categorize certain photos, and some of the results are quite frankly laughable.
Yes.
But a human being would immediately see the error.
Exactly.
However, it will sort out a whole bunch of photos into people and with a few errors there, and you kind of
Exactly. That's a very good point. And that's actually one of the, we're kind of going back now that we went too much into the way of using algorithms for everything. And now we're saying, okay, actually humans are useful. We should have a human in the loop making decisions.
Exactly.
So there's a huge area these days, like human in the loop artificial intelligence.
Okay.
Explain to everybody what an algorithm is.
So algorithms is, so in the context of artificial intelligence, it will be a computer program that can take data and an objective function, some way of evaluating how good it's doing, and it can learn how to better make predictions. That will be an AI algorithm. Take data and produce and learn through trial and error to maximize some function, let's say, minimize the errors or maximize the benefits of some sort. Okay, so I think I'm a little I'm running out of time, so I'm gonna move.
Is there going to be a test afterwards?
Okay, but there is this general trend. The general trend is that in the past we have simple programs with not a lot of data, and humans were very important in defining the steps of the computer program. Okay, but then as we got more and more data, the human designer of the computer program became less and less relevant, and we can use more of the data. Okay, so let me just show you one example of that, and then one example from my own research to convey this idea. So here is a model. You don't need to go know the details, but this is a model that was designed by a human. Say, okay, this is how a computer should recognize speech. Like when the computer hears something, this is how it should transform that speech into text. Okay, so the model is saying, okay, this is how you take each of the samples of audio, and this is how you combine them. So it's very detailed, and it's very easy to understand. Now, this is a model that was proposed at Baidu. This is like the Google of China. And it's a very, very complex model. I won't go into details, but suffices to say that this model has billions and billions of parameters. Okay? So these are huge models, huge computer programs that actually don't fit in one computer. They need to run these computer programs in a cluster of computers. Okay? But because they have a lot of data, they can run these computer programs to make speech recognition to be almost as good as humans. So here's a comparison. This is the model that they run. This is the error. So smaller is better. This is the human error. So 5%, 8%, 5%. And the computer program that they run achieves like near better results than humans. And there are some tasks. Let's say this task is especially challenging because there is a lot of noise. So the computers are still having problems when you are talking. Let's say you are driving and you're talking and asking someone, let's say customer service. You're trying to ask something like when you have a lot of noise in the background. That's challenging for the computer. Activity recognition. So in the past, let's say. Some people have the idea of using cell phones to recognize what you're doing. Right? So that might be useful for several reasons. It might be useful to, let's say, for people that have some health problems, it would be useful to know where they are, what they're doing. But we don't want them to always say, I'm here in the library, I'm in the, in webcast. We want the cell phone to automatically do that. In the past, we use several features to make that prediction of where you are. There was GPS, the audio, so the cell phone was recording all the time what you were doing. The Wi-Fi, what were the apps that you had open and things like that. So this is a research that I did with one of my PhD students, and because we had access to a ton of data on what people have done, we have access to 2 billion seconds of activity, we were able to learn this much better, and now we don't need a lot of, let's say we don't need GPS and we don't need audio to make predictions of where you are. So the predictions are a lot better. Okay, so I'm gonna move quickly here into some ethical aspects of artificial intelligence, because artificial intelligence is being used these days for more than just classifying cats and doing things that are kind of silly. We want them to do more useful things, like let's say helping in the relief of problems. So there is a huge concern these days because the data that we are giving to the computers were generated by humans. And we know that humans have biases. And we know that the data is being generated by certain populations, right? Let's say the data is being generated by people that have computers, right? First of all, people that use Google, people that are in the West Coast, in Silicon Valley, those are the people that are generating the data. So the algorithms are picking up on human biases. So here, so there was a big paper this year revealing that computers that learn from Wikipedia, for example, they are biased against women because they think that women are closer to being nurses than to being doctors, for example. That men are closer to being engineers than teachers, for example. Okay? So if you have, so now there is a big concern because we need to make sure that algorithms don't pick up on the biases that the data has. Here, Google Photos, I think someone mentioned Google Photos. There was a gentleman that realized that Google Photos classify humans as animals. Right? So if the person searched for certain animals, some of the pictures of him and his friends will come up into a computer. So it was a huge problem. Here I have another problem of a computer program trying to detect whether the picture is correct for a passport. Okay, so one of the things that we want to check is that the person doesn't have the eye closed, right? So there was a computer program running on a web browser, and some people, let's say from certain races, were detected, were flagged as having their eye closed, when in fact, it wasn't like that.
So hold on. Apple has just come out with a phone device, number 10.
Yes.
That has face recognition.
Right.
Is that face recognition matter part of the artificial intelligence world?
Yes, because in the past, well, that's a little bit even more advanced than face recognition. So face recognition is saying, okay, in this room, if I take a picture, there are 20, 30 people. Okay, here they are. But they are doing face identification. So based on a face, they're saying, this is Daniel, based on my face. And they're using very sophisticated measurements. So they're trying to say, this is the identification of someone. So that's even more complicated, and it might bring even more problems. Okay? So there are all these biases that computers are picking up. There are other problems, let's say, with self-driving cars. Like what's going to be, like if a self-driving car crashes, it's going to be the fault. It's going to be the driver at fault. It's going to be the software company that created the self-driving software. Is it going to be the company that provided the data? Like who is at fault if there is a crash? If someone dies. There are some websites that offer you credit, right? If you go to Amazon, or I think I bought a computer a couple of years ago, and I had an offer of a credit. If I get this credit card, I will get a 20% discount. I fill out the form, and I get an approval in 10 seconds. Okay? So what those websites are doing are actually running a computer program that take all of your information, where your filling out the information from and all the, you know, the name, the income, and all this, and combining them with data that they had from the past, and predicting whether you'll be a good someone who will pay the loan, right? Essentially. But some people are not as lucky because I got the loan approved, but some people are not as lucky and they get rejected, but they don't know why. Right? In the past, you could ask, and there are some laws that you can ask, why am I getting rejected for this loan? But the problem with these big computer programs is that they don't know how they are coming up with a solution. It's very hard to know how the computer program had this answer. In the past, because the models or the algorithms were simple, it was easier to do. And the European Union actually is thinking about creating a regulation, and they call it the right to explanation. Okay, so they will require all these companies using automated systems to provide a human understandable explanation of why they get rejected for loans or why they got profiled for an arrest or things like that. There are a lot of jobs that are going to be lost because of artificial intelligence, especially jobs that are very easy to automate. And this is a prediction. It's a little bit, I don't know if it's too optimistic for my taste, but it's kind of on the right track. So let's say, so these are prediction of what are the jobs that are going to be lost to robots, to AI, in the next 20 years. Okay, so telemarketers, accountants, salesperson, writers, real estate agents, all of those people have more than 80% chances of losing their jobs. But then you have people like recreational therapists, dentists, athletics, that have very little chances of losing their jobs. And this is because all these tasks that are here are very easy to program, are very easy to put into step-by-step solution. Let's say accountants that need to check, you know, that everything is matching, and they have to look at a rule of a set of rules to come up with the discounts and things like that. Yes?
Aren't we developing a very fertile field for hackers here?
For what?
Hackers.
Oh, hackers, yes. And that's kind of goes into what he was saying, like there might be hackers that might impersonate someone, might generate data about someone. Like there is this proposal that I put trying to see if we can actually generate the voice of someone. What if I record you for a couple of seconds, and then I create a computer program that can generate whatever I say with your voice, and then I call your credit card company.
We're almost defenseless, though.
Well, people are working on ways of dealing with these problems. So there are actually companies and governments trying to come up with ways of protecting against this kind of problems. So at the end, we'll have AI protecting us from other AI systems.
So if they can hack Equifax, I mean, that's wide open.
Yeah. Well, that hack was really
That's
actually,
supposed to be
if you
secure,
read at what they
right?
did, it was so simple. It was just almost, I could have done it. Like, it's just the security that Equifax had was not that great. So it wasn't such a sophisticated. The weakest link usually in security protocols are humans themselves, because they trust.
How often are law enforcement using this, and are they being trained to use artificial intelligence? Do you know?
Well, I don't know how much they use it. I know I lived in Chicago for a couple of years, and they have an AI system to predict which restaurants to visit for health inspections. That has a bunch of problems because they were using data from the past, right, to make these predictions, to learn what are the areas and the times of the year that they should visit. And I think what I get is that the training that law enforcement have is not that good. They need to, realize that there are biases, that the data was generated by humans, that humans are biased, racially biased, and gender biased, and things like that. So we need to. So what's interesting here, this is the last point, is that all these things that require a lot of being very precise with your hands are very hard to be replaced by robots, because we don't, the complex, let's say being a dentist is very, very hard
How does,
for a computer.
how does artificial intelligence play into robots?
Yeah, so that's, I've been talking mostly about the mind of a robot. Like the robot needs to have, on top of having a good, good predictions, it needs to have some way of actuating in the real world, right? So there's been some research in that there are some impressive results on how robots learn, but the actual motors and the actuators, that actually moves a lot slower than what software can do. Okay, so we need a couple more. I don't know. I'm not an expert in the area, but we need more time to get the precision. I mean, we don't have a robot play the piano. It's like one of the pinnacles of the human body, and we are not really there yet. I don't know how long it will take, but it's really complex. Yes.
If we had a cyberspace interruption, would all of this be dead in the water?
You can think of these systems as just software. So if software and computers are attacked, then yes, like all these things live in the same space as computer programs. So there are all these weapons that are aimed to extract circuits and how computers work. So if
It needs that energy to operate.
they need energy,
And if it's not there,
yeah.
okay.
Yeah.
Where'd you learn that expression, dead in the water? That's a hip expression.
I have kind of a futuristic question. I look upon AI as test tube babies. And I've read about recently that some AI will be created in the future that will be superior, that they, in a sense, program themselves. But my question is, they always use the word mind and think with AI, but also emotions are attached to most of our thinking. Do you think in the future they will create an AI that will incorporate emotions into their thought patterns? Just your opinion.
Here's my opinion. So my opinion is that there are two opinions.
Okay.
So one opinion is that machines weren't, like there is something intrinsic, biologically intrinsic about us. So love, emotions and all those things will never be able to be recreated by machines, because there is something biological that was, that we have intrinsically that cannot be reproduced. And the other view is that everything that we feel is just, electrical signals in the brain. So love, emotions, so why not? Why can't we just create a computer that can reproduce those things? And my view is kind of in the middle, so it's not in either of those. So there are certain things that I think we'll be able to reproduce, like compassion and things like that, because I think there are some real value. I mean, of course, there is some real value to having those goals in a system, because that's how societies work, and that's how, I'm not gonna get philosophical, but essentially, we as society has come up with things that are important. We don't really know why compassion, maybe we don't have a good explanation of why, suffering is important, but I think those things are important, and AIs will need to incorporate some of those things into their...
Yes, well, if there's ever going to be ethical questions involved.
Yeah, now, if I think that there will ever be a machine that can kind of self-learn and improve and achieve some sort of superhuman level of intelligence, I don't think so. Not in the lifetime of, I don't know, I think it will take thousands of years, but I'm not gonna be here, so.
Where would politicians come in? Maybe replaced.
Well, that's a good question. So are they actors? So actors are here. Are there telemarketers?
Do you have anybody particularly in mind, man?
Yes, quite a few.
Yeah. Are there clear?
Well,
so
decision,
it's very
decision making.
What they do is very complex. So they need a very good model of what people are thinking, a very good model of other people's minds. They need very high social skills. Those are very hard to produce. So not anytime soon, I think.
So let's just hope.
Not for 2020 at least.
Will it be before the next election? That's really the time frame. One or two things. We have now provided cough drops over there for guys who have postnasal drip in their little throat aggravation. And I suggest you know about it. Over there also is a bookmark that tells you what the schedule is going to be for the following 4 weeks or 5 weeks. We are going to create a survey about a bunch of questions. That will contain a bunch of questions about your objectivity and your sense of the value of the series. And also do some rating. And also going to ask you, what subject matters do you want to know about and learn about and be informed about? And who speakers, what names of speakers that you would like to be, would like to invite. Think about the limitations of that part of it. We do not pay for speakers. Guys from out of town are not going to come here. Joe Nacera is not going to come here. A bunch of guys that I deal with, they're not going to come here because we're not going to pay their airfare. So we should have that together, we hope, by December 1st or something like that. We'll send you to you. We hope that we'll be able to fill it out on the computer with some X's and O's and things like that. I can't thank Danny enough for coming here and trying to explain what AI is. There'll be no test afterwards.